Hello, I'm François, a principal performance engineer in the GraalVM team at Oracle Labs Zurich, and I will talk today about performance tuning in GraalVM Native Images. So first of all, what is GraalVM? GraalVM is a Java virtual machine like any other, but unlike others, it is a high performance virtual machine with also extra capabilities like ahead of time compilation, among others. Ahead of time compilation is the process of turning Java files into standalone binaries, meaning executables that do not require any JVM or anything else to execute. There are many benefits in using GraalVM Native Image. One of them is that the packaging size is much smaller, and because you do not need a JVM for deployment. So say you are using containers to deploy your applications, you do not need any JVM in it, you just need your final binary. And even if you decide to statically link all the shell libraries within your executable, you do not even need an operating system to run. So this is very, very interesting for cloud deployments. Another benefit, also relevant in cloud deployments, it's instant startup, because unlike the JVM, no warm-up is needed. It can start right away because all the compilation, everything has been done upfront, and you already know on which operating system and on which architecture you are running. Another benefit is memory footprint. The JVM, when it starts, it loads all kind of JDK classes. It does plenty of initialization with class loaders, etc. But with native image, there's a closed world assumption. Everything is known up front, everything has been built up front, and you only have machine code ready. And it means that your memory footprint will be smaller. So how can we get GraalVM? If you go to graalvm.org, there is the documentation, there is the overview of everything you need to know about GraalVM, and this is also where you can get it. You can download the GraalVM Community Edition, or you can download the GraalVM Enterprise Edition. In terms of features, they are very close with each other. The main differences is that Community Edition is open source and free. The Enterprise Edition has many compiler optimizations baked in that are not available in the Community Edition, meaning that you can get extra performance benefits with this version. It's also available for free in the cloud, in Oracle Cloud, and since Oracle Cloud also has a free tier, you can basically use it for free today. Now, the goal of this talk is to talk about performance. Now, to measure performance, there are two things we need to define. One is we need a benchmark, an application that we will use to simulate and to emulate a real-world workload. And then we need to measure something out of it. It can be throughput, it can be your memory footprint, it can be anything. And for this, as I mentioned earlier, GraalVM Native Image is very interesting in the context of cloud deployments. And in cloud deployments, what is very popular nowadays is microservices. Microservice frameworks, there are popular ones like Micronodes, Spring, or Quarkus. Today, I have picked Spring as an example. And the Spring guys and Spring Boot framework developers have come up with pretty complex demo application that is called Pet Clinic. It basically, it is a web application, several pages, endpoints where you can interact with a database of pets and owners and do all kinds of operations with this database. What we have done now is that we have taken this application and use a load tester tool. We have taken the WRK2 tool to apply load to different endpoints to simulate actual workload to this Spring Pet Clinic app. We will send 1,000 requests per second. The idea is to send as much as we can as the application can handle. So the tool by itself will try not to overload the application too much, but you can define a time range where it will try to get the maximum throughput out of this. And in this process, it will measure the response time of every single request, what we call latency, and it will also measure the throughput, how many operations per second have been done. So we already have two metrics here to analyze performance. So let's look at performance of the GraalVM Community Edition versus the GraalVM Enterprise Edition. In this slide, I show the Community Edition in the graph in blue and in the Enterprise Edition in orange. The chart we see is what we called a latency graph or latency distribution. This is an aggregate of all response times that we have seen across the duration of the experiment. Basically, a more common term to talk about percentiles, if you look at the 50 percentiles, it is what we called the median. The median is half the response times are lower than this value and half the response times are higher than this value. So if you look at this chart, GraalVM Community Edition may be around 3 milliseconds median, so the 50 percentile. Percentiles in latency graphs are very interesting to look at performance because you can see the fastest responses, you can see the slowest responses, and you can see the point at which there's some kind of inflection point. Here it's around the 90 percentile, where all of a sudden we get a steep slope where the performance degrades. This is quite usual to have some performance, some percentage of requests being answered with more time, in this case like 2 or 3x more time. It's usually when garbage collection happens. So if we compare GraalVM Community Edition and Enterprise Edition, you can see in the chart that in the full latency curve, GraalVM Enterprise Edition is outperforming the Community Edition. This is thanks to the extra optimization the compiler has. Overall, the throughput is 23% higher, meaning that in this case, we are processing 9,000 operations per second versus 7,500 with the Community Edition. The memory used is also 18% less. Even though we are processing more requests per second, we are consuming overall less memory. And the binary size is also smaller because we could, with smarter compiler optimizations, we could eliminate more code, meaning the final binary is smaller. Basically, some object allocations have been completely removed because they've been proven at compile time that they were not necessary at all. Okay, what can we do to drive performance further? That's the whole goal of this presentation, is to see how we can get more performance and how we can tune this. So GraalVM Enterprise Edition has a feature called Profile Guided Optimization. We call it PGO for short. And it's a special way of compiling your application by feeding extra information to the compiler. Basically, runtime characteristics about how the application behaves. What we do here is that we compile the application first into a native image that contains special code, instrumentation code, that will collect statistics for you about those runtime characteristics. Those mainly mean the hot methods, What we call honk methods is the ones that have been called many times throughout the application execution. The honk methods are the ones that are the most important performance-wise. The method that have been called once or twice, it's not worth investing a lot of time in the compiler to optimize them. So we will collect those statistics, and then we compile the native image again by feeding those profiles to the compiler. And then the compiler can be much smarter at compilation time by leveraging those information and spending much more effort on the hat method, giving more budget, taking riskier decisions like duplicating code, unrolling loops, those things that can be costly in terms of binary size, for instance. But it's definitely worth it if you can get several tens of % better performance just by over-optimizing one or two methods. On the other hand, you can also decide to reduce the effort on some cold methods, because there is no point in doing fancier optimizations if the method is called once. Okay, so let's run this Spring benchmark again with GraalVM Enterprise Edition and PGO and look at the numbers. Here are the results. The Community Edition is still visible in blue, the Enterprise Edition in orange, and the Enterprise Edition with Profile Guided Optimization is visible in green on this chart. So what we see is that most of the response times are now even lower, and the green curve is below the orange curve almost throughout the whole latency graph. What we notice is that the throughput goes up by 32% compared to Enterprise Edition, which was already 20% faster than Community Edition. Then you can see that we are consuming a bit more memory, 11% more, which may sound surprising, because if we are doing smarter compilations, why would we measure higher memory? The reason is fairly simple, is that if we look at throughput, we are processing 32% more requests. So basically the memory we use per request is still much lower, because we only increased memory by 11%, but we increase our throughput by 30. So we already have an improvement in memory footprint, even though the numbers at first glance would look like the opposite. We need to think about how the benchmark is designed, and it really tries to maximize the throughput during a period of time. We also see, as I explained earlier, that the binary size is smaller, and this is thanks to the compiler being smarter, thanks to all the profiling information. Okay, this is great. We have seen how we can reduce latency greatly. Something I would like to talk about now is about the tail latency. What we call the tail latency is the point from which the performance starts degrading in the percentile, and from which the percentile gives a worse performance. In this case, looks like Community Edition, Enterprise Edition, and even Enterprise Edition PGO, they all seem to have a change in behavior around percentile 90-ish, where latency is around, it's below 5 for sure, it's around like 4 maybe, and all of a sudden the P95 or P99 degrades very quickly, and we see this bad what we call tail latency, so a big portion of the response times being worse in performance. As I mentioned earlier, the reason for this is garbage collection. We spawn so many requests, the application is under heavy load, so it allocates a lot of memory, and we need to free this memory at some point. And this is the point of having garbage collectors. So the good thing is that in GraalVM Enterprise Edition, we also have the G1GC garbage collector available. And the G1GC is also available on the JVM. It's a garbage collector that works in the background. It runs in parallel with your application. There is a constant overhead of having the garbage collector running, because it does the job in the background, but it avoids at all costs the full GC poses and tries to optimize for low latency. It really wants to avoid having poses that will hit the response time of some requests. And this is the main advantage versus using a lightweight stop-the-world GC like Native Image ships by default. There has been the choice of shipping the lightweight stop-the-world GC because in many cases, would I say, the memory intensity, the memory write locations are so many in applications. In some cases, you may want, you may not need more advanced garbage collectors. So the design of Native Image has been done in such a way that we can limit the overhead as much as possible in order to favor like small binary size, very quick response times, etc. So let's look at the numbers using Enterprise Edition G1GC versus Enterprise Edition. Here are the charts, and you can see that the tail latency looks much better. Now we start going up slightly around percentile 95, and it doesn't degrade too bad. And even the max latency is around 10 milliseconds, which is not more than 4x the best latency. This is within reasonable bounds. And if we look at the throughput, it goes up by 9%, just because of all this time that we do not stop the world in the regular GC. The max RSS, so meaning the memory footprint, is similar in these two modes of execution. So despite having higher throughput, it means that we still have a reasonable memory footprint. But the pain point is that we have a much larger binary by 27%. In this case, it's close to 200 megabytes, while the default version is 150 megabytes. So you need to take that into account if you're really optimizing for small binaries and you do not care so much about peak performance. Maybe you do not want to use the G1GC garbage collector. Okay, so we have seen how we can use profile-guided optimization to let the compiler take smarter decisions. We have seen how we can use different garbage collectors to get rid of the tail latency, also at some cost. What if we use both now? Well, the benefits sum up pretty well. And as you can see in this chart, the GraalVM Native Image Enterprise versus GraalVM Native Image Enterprise with both PGO and G1GC has a much nicer latency curve in all aspects, meaning that the median response time is better. The overall throughput is better by 40%, which is significant. Like in this case, it's 30,000 operations per second versus 9,000 operations per second. It uses more memory. In this case, it is still better in terms of memory per request, because we increase the memory not as much as we increase the throughput. So we still have a benefit there. But we have a slightly larger binary. PGO actually brings the binary size down, but G1 will bring it up a bit more. So this is why we end up with a binary 12% larger. So in this case, it's 170 megabytes versus 150. Okay, so then something we need to be aware of is that garbage collectors can also be tuned, and you need to define what are your goals. If you really want to get rid of the tail latency, you can, but you will need to accept the fact that you are using way more memory and that you are more greedy in memory. And but this is acceptable. And then on the other hand, you could decide to be more restrictive in terms of memory, and then you will lose a bit of throughput. This is what we can see in these slides. Chasing the right metrics is really important to know what one wants to optimize for. Because if one says, I want this application to perform well, the first question is, what is performance? What kind of metrics you're after? Are you trying to minimize memory footprint? Are you trying to maximize throughput? Are you trying to maximize deployment time? Are you trying to maximize the time to the first valid response from the application? So all those aspects are important, and you need to define that before actually trying to optimize anything. Moreover, just like on GraalVM, we should always, if we are on a performance critical application, we should always tune the max heap size and set a value for the command line flag XMX. The higher this value is, the more relaxed we are, the larger the memory footprint will be, but the better the throughput. So we are okay to allocate a lot in order to have very low pause times. In this case, that will mean small tail latencies. On the other hand, you can have a low max heap size. In this case, you put a lot of memory pressure on your application. You are forcing lots of GC from happening, and your tail latency with loop works, and your throughput will be worse, but we will be saving quite some memory during runtime. So it means that one has to answer what is acceptable for the application. We need to define SLAs, service level agreements. And one example question is it acceptable that 5% of the request, meaning the P95 value, is 5x slower than other requests under heavy load? If this is fine for one's application, then we can tune accordingly either the GC that is being used or the heap settings. Okay, that covers all the aspects of this talk. So as a conclusion, consider using profile-guided optimization to let the compiler do smarter compilations. Consider switching to G1GC if your application is memory intensive. Do not do it if the microservice, for instance, is very simple and does not allocate a lot of memory, because in this case you will have a lot of overhead by using the G1GC garbage collector, but without the benefit, because your pause times and your tail latency will already look good if you are not in a memory intensive scenario. And always tune max heap sizes to increase or decrease memory pressure in order to decide what is acceptable or not in terms of throughput. Okay, this concludes my talk. Thanks for joining this session, and enjoy compiling native images.